In item 3 on the first exam for spring 2015 from Strength of Materials, we're given that we have a bar that has material stress strain curve that is pretty ductile, and we don't know that it goes out to rupture here, but let's see what happens in the situation to see if we really care or not. It's a 3.5 inch long bar. It's pulled until its total stretch is 0.0525 inches. So its original length is 3.5 inches, and its total deformation is 0.0525 inches. And then the load is removed. Find the length of the unloaded bar. And I look at that and I wonder, gee, I have no idea, even though that seems like a really small number. I don't know if that represents a elastic stretch or whether or not that would actually involve some plastic stuff. So that's what I got to first figure out, just how much total strain are we looking at here. So our strain is just equal to our deformation over original length, right? And so that would be our 0.0525 inches divided by 3.5 inches, and that would give us a strain of 0.015 inches per inch. And so that tells me that, okay, I'm going to go up to our stress strain curve, and when I do that, that stress value puts me well into the plastic region. And if I read this carefully, that stress that's associated there is 28 KSI. So that means that the way this thing behaved was that it was loaded up from nothing, and then it hit a yield point right there at 20 KSI, and then it kept going all the way out to a total stress of 28 KSI, or really a total strain of 0.015, and then it was unloaded. And the way it unloads is at the same as the elastic. So that means that I need to draw a parallel line there, and I'll have to figure out what's going on there. Right? Alright, so that's good. I found out a lot of things here. I'm going to need to calculate what the elastic modulus is, because the only way I can figure out in a nice precise way, I guess I could do it graphically, but what I'm trying to get is this final deformation. There's my permanent or plastic strain, and I know what the total was, but when I let go of this thing, unload it, I'm going to have a little bit of elastic recovery. And so I need to figure out what that's going to be. That's an EL for elastic. And so that's where we're headed here then, is to figure out what all these little pieces are. The elastic modulus, it looks to me as though we have the yield point right at 20 KSI, so that makes this easy here. These gradations are 0.001, so our elastic modulus is going to be stress divided by associated strain in the elastic region, and that would be then 20 KSI divided by 0.001 inch per inch, and that makes then our elastic modulus equal to 20,000 KSI. And so now I don't have to guess what happens here. Presumably the only guessing here is reading 28 KSI as close as I can. It's a little bit above the midpoint, so it's above 27.5. So my elastic recovery here is, well, how much strain do I get out when I unload this thing? That's what we're going to be trying to calculate here. So that strain, that's basically Hooke's law in that region. Okay, so that's going to be our stress divided by our elastic modulus. That now, because we're way out there, but we do have strain hardening, I guess. It's not really strain hardening, we just have a positive stiffness or slope to the stress strain curve out in the plastic region. We get 28 KSI divided by 20,000 KSI. That's really per inch. And when we work that out, then we will get a elastic recovery strain of 0.0014 inch per inch. Okay. Now our plastic strain then is going to be equal to our total strain minus the elastic recovery. So that's 0.015 minus 0.0014, and that will be 0.0136 inch per inch. And that means that our plastic deformation can be found directly from our plastic strain. That's just going to be our strain P times LO. Now, if you wanted to be a little bit more sophisticated, you use your L final to go figure this out. But first order theory says we're going to do everything based upon the original configuration, assume that everything's small, that the error that we introduced there is of a very minor type nature. And generally speaking, it will be, and you'll see here too that this is pretty small. Just under 0.05 of an inch of plastic deformation. So that our final length, our answer in this problem then, is going to be that our final length equals our original length plus our plastic deformation. And so that'll be our 3.5 plus 0.0476. And of course that will work itself out to a nice simple addition of 3.5476 inches, or approximately 3.55 inches for the final length.